对啊，你跟助教联络一下，应该可以补教。对啊。
助教是谁？
肖登红，他现在好像没有在教室。
好的。
我应该写你的。反正你在嘉兴上嘛，所以课程网页上有你跟邓红联络一下。就是你有寄信给我吗？对，OK，那我看到信。Hello. Okay, I guess that's time to start. Any question from this time? And if not, today we are going over determinants. Okay. And well, here the definition of determinant, and I guess it's back a bit. And first is a bit of a review of determinant. Determinant is a number that you can calculate from any square matrix. So any n by n matrix, you can calculate the determinant of A. And its most important property is that determinant will tell us whether a matrix is singular. If determinant is A equal to 0, then A is singular. And if it's not 0, A is not singular. Okay. And then there are two notations we have for determinant. One is dot and parenthesis A, and another one is just put two straight lines and the numbers of A. So the two straight lines 3, 4, 2, 1, and is determinant of A. And for 2 by 2 matrix, we know there is an easy way to there is a the formula to calculate determinant is quite easy. It's you multiply the diagonal together, then you subtract the off diagonal product. So it's 3 times 1 minus 2 minus 4 for this example, and that's minus 5. Okay, and yeah, sometimes determinant is 0. And let's go back to the definition of determinant, and we define the value of determinant by recursively, and so this recursion is quite complicated. And here we have the definition where we expand on first row of determinant of A. Okay, so what we do is we will take each element of the first row. So maybe let's go here. So we take the first element of every element of the first row and have those elements. So it's A11, A122, A1n multiplied by cofactor. And the cofactor is something you can calculate from n-1 by n1 semi matrix. It's the submatrix. And here, so after I think about this, I change the notation. And so those cofactors in the book they are called Aij, but we also say we would like to denote Aij as just the ijth element of A. And so I decided to change everything here and rename this cofactor as A to a Cij. Okay, so in the slides I will try to keep A Cij. And in homework, I think it's better for you to also keep this notation, but yeah, but we will try to. We will try to accommodate you if you actually mix up, because in the book it's Aij, so hopefully this is not too confusing. Okay, so I guess in the homework you can use either notation, but I prefer you also say Cij. Okay, and I guess maybe if we talk about notation, that maybe let's talk a little more. So I look at Wikipedia, and sometimes people also do Cij. Okay, so maybe let's write here. Okay, so although sometimes it's Cij. So in our book, people will write Cij here. Okay, so that's the annoying part about definition, about the notation for cofactor. And well, we have this ACij now. And how is it defined? It's defined by, so for every ij, it's -1 to the ij. So you have -1 depend on, or no -1 depend on whether I plus j is even or odd. And the determinant of a smaller matrix. So this is why this is a recursive definition. So determinant of n by n matrix is defined by how determinant of n-1 by n-1 matrix is calculated. And yeah, and the base case when n equal to 1, determinant is just your element a11. And what's this matrix? We have a very graphic example here. So submatrix is just, so you take some ij, and so you cross out the row with this I and the column with this j, and you're left with n-1 by n1 matrix. So you put the 4 remaining blocks together, then that's your mij submatrix. Okay. And yeah, so let's just say again. So this cofactor ACij is -1 to the I plus j determinant of mij. And mij is n-1 by n1 matrix. You get it by deleting row and columns. Okay. So you delete row and columns. Okay. Any question about the definition? So this is a quite cumbersome definition we have for determinant. And anyway, let's see that this is actually the same determinant that we learned in high school. So for this 2x2 case, if we expand on the first row here, so we have a11, and oh, sorry, here I forgot to change. There is many ACij I should write. So those should be all ACij. Okay, AC. Okay, and yeah, in this case, so we have A11, AC11, and A12, AC12. If we expand on the first row, then then we need to see what's AC11. So for for the 1, 1 element, the submatrix is to delete the first row and the first column. So the remaining matrix is A22, and so AC11 is just so -1 to the 1 plus 1 is 1, and the determinant of A22 is just A22. Then we have this AC12 is you take this 1, 2 element, and so you delete this row, this column. The remaining matrix is this A21, so the determinant is A21. But now you have this -1 to the 1 plus 2 equal to -1, so you have the extra minus sign here. So in the end, you see that this is A11, A22 minus A12, A21, exactly as what we expect. Okay. So this is a cofactor expansion. And then we keep saying that we are expanding first row. That's because we can expand on any other row in the column. Okay. So we can also expand second row. So if we expand second row, so we have A21, and we want AC21, which is this element with a minus sign. Okay. So that's just A21 times minus A12, and that's this thing. And then you have A22 here, then its cofactor is just A11, because it deletes this row in the column, it's become A11, and this is A22 and A21. And not only that, you can see that you can also expand not only rows, you can expand on any column. So you take a column, and then you take A11 times cofactor of A11. So this thing is the same as when you expand on row. So A11, then AC11 is A22. Then you take A21 and AC21, then it's this once again A12 minus A21. Sorry, A21 minus A12. And similarly, you can expand on the second column and get the same determinant. Okay, any question? And I don't think we give a proof, but this is true for this determinant that you can determine is equal when you expand on any row in the column. This is true for matrix of any dimension. Okay, and let's have a bigger example. So we have determinant of 3 by 3. So here we expand on first row again. So this is 2, 2, 5, 4, 3, 1, 2, and 5, 4, 6. Excuse me, 5, 4, 6 matrix. Then we expand on first row. Then we have A11 equal to 2. Then cofactor of A11. Cofactor of A11 is this determinant of this matrix 1, 2, 4, 6. Then we expand on this A12 equal to 5. Then because it's 1, 2 element, you have a minus sign. Then the remaining determinant is this 3, 5, and 2, 6. Then we have A13 equal to 4, and the determinant of this matrix 3, 1, 4, 3, 1, 5, 4 here. Okay. And you can calculate this. It's and you calculate this out, then you get a number here. And similarly, you can expand on the first column. You have 2 times once again this submatrix determinant of this submatrix. Then minus 3 times the determinant of this submatrix 5, 4, 5, 4, 4, 6, and plus 5 times the determinant of this submatrix, etc. And also just a reminder of the high school, if we expand out everything, you see that these are 3 terms minus 3 terms. This is the formula you probably learned for 3 by 3 matrix. In high school is you take the product of the 3 diagonals, so this 2 times 1 times 6 plus 5 times 2 times 5 plus this 4 times 3 times 4, then minus the 3 of diagonal. So 2 minus 2 times 2 times 4 minus 5 times 3 times 6 minus 4 times 1 times 5. Okay. Yeah, so this is also a formula that's probably a little faster. You can calculate for the determinant of A, and it will equal to this row and column expansion. And but I guess I should say a little. So this diagonal and off diagonal calculation only works until dimension 3. Okay. So let's write a little bit. So the diagonal calculation. Diagonal calculation only works for n less equal to 3, but it's a nice quick way to do calculation when you have a smaller matrix. And yeah, when n equal to 4, then you have many remote terms, and then you need to actually do the expansion thing. Okay. Okay, so that's an example of calculating determinant. And now let's see properties of determinant. And the first property is that we can expand the cofactor using any row and column. And I don't think we will prove this, but this is true. I guess if you really write down the expansion into individual terms, you can prove it, but it's quite a bit of writing, so let's just state it here and know this is true. Okay. And yeah, so the proof itself is not so important. You can write, you can brute force out expansion, and actually you will get another expression for determinant. But anyway, there is a proof, and but let's see that what we can learn from this proof. And so first is since we can expand the cofactor in any row and column, then we can choose the row and column to make our expansion easier. So for example, we have our A equal to this matrix. Then we see that there are a whole bunch of zeros here, and when we expand on a row and column that has a lot of zeros, there are much less calculation we need to do. So for example, we expand on this first column, then there are 3 zeros here, and so when you multiply those zeros, you don't need to calculate the cofactor with this 0 because you are multiplying with 0. And so when you expand the first column, you only need to calculate the expansion with this element. So that's a minus 2 times the determinant of this submatrix here, and so let's mark a little bit. So expand here, then maybe this is better. So you expand here, then you only need to calculate this matrix. Okay. And and then in this matrix, once again you see you have this column that has 2 0. So expand here, then you only need to calculate this element times so that's 3 here times the determinant of this matrix. And then you calculate this is 10 minus 12 is minus 2. So this is minus 2 times 3 minus 2, and the determinant is 12. Okay, so this property gives us a better, easier calculation sometimes when we have a whole bunch of 0 in our matrix. And also, this expanding from any row in the column property let us prove that determinant of A transpose equal to determinant of A. And I guess, yeah, here we have proved by induction. So basically, because we have A transpose and A, and so if we expand A on first row, that will be same as expanding AT on first column. Okay, so AT expanding on first column. Well, you see you have all those same small a elements. So I have A11, A2 to the A1n, and A11, A12 to A1n. And then we prove by induction because then we have cofactors that are determinant of those n minus 1 by and yeah, so I guess let's take an example. So the first term here will be this yeah, maybe that's right. Okay, so the first factor you have expanding is A11 times the determinant of this matrix. And for the determinant of AT, you also have A11 here, and then you need to multiply with the determinant of this submatrix. And you see that here, these two submatrix are also the transpose of each other. Okay, so here we have proof by induction because the definition of the determinant is defined inductively. And so we need to have the transpose determinant of those two smaller matrices are the same. So this is transpose. Determinant of this transpose equal to the determinant of this transpose. Okay. Then the determinant of big A will equal to determinant of AT. And so we can go go from every n by n matrix. We can go from any n by 1 and n by 1 matrix, determinant of it equal to its transpose, then every n by n will be the same, and then we go all the way up to 1 by 1, and in the base case we know determinant of then in the 1 by 1 case the matrix is just A11 and A11 equal to A11 transpose, so their determinant is the same. Yeah. So that's a whole bunch of yeah, that's a derivation for this theorem. Yeah, yeah, I guess any question? Yeah, I guess the detail you can fill out. And yeah, here is a bit of example. You have two matrices, and you can do it yourself. When you really expand on it, you see the determinant of the same, and the expansion on first column, first row is really same as the expansion of the first row here. Okay. And the next one we have sorry, too much. Okay. And next one we have a bit more interesting theorem. So we have the determinant of any triangular matrix equal to the product of the diagonal element. And remember what a triangular matrix is: a matrix where either the lower triangle or upper triangle equal to 0. So here we have upper triangle matrix, which means the lower triangle are 0. Okay. And then we have I guess we don't have a whole proof, but basically you can keep expanding on the columns with a bunch of 0, or yeah, if the upper triangular matrix, you keep expanding on columns with lots of 0. So you expand on first column, that is 1 times this matrix, then you expand on the second column. The first column of the submatrix, then is 2 times this submatrix. Then expand on the first column again, is 3 times this submatrix, and it's just 4. So you see that expanded is just A1 times A2 times A3 times A4. Okay. Okay. Any question? And here, I guess we smuggle in a bit of another definition of determinant once again. This will not quite used, but it's a bit nice to know. So if you really write down the definition of determinant into all elements, then you will be sum over all permutation of a number and A1 A1 sigma 1. So the sigma is a permutation. So the sigma 1 to sigma 2, sigma 1, sigma 2 to sigma n is any ordering of the number 1 to n. Okay? And so you have all possible ordering, and this product of A1 sigma 1, A2 sigma 2, and sigma n together times the sign of the sigma. Okay? So sigma some permutation of 1, 2, 3, 4. So for example, you can have 4, 2, 1, 3, and so there will be n factorial different sigmas. So yeah, so there are n factorial different sigmas. Okay. And so you really expand all those all those covector expansions, then you will have n factorial different terms, different products summing together. That will be your determinant. And for example, when n equal to 3, then you have those 6 different ordering. You have 1, 2, 3, and 2, 3, 1, 3, 1, 2, and 1, 3, 2, and 3, 2, 1, and 2, 1, 3. And yeah, there's some way to define the sign, and if you really want it, you can look out in Wikipedia. Okay, so that's a bit of digression. Let's go back to our book material. So more theorems about our determinant. And then now we have a nice theorem saying that you have entire row and column equal to 0, then determinant equal to 0. Okay. And also if you have 2 rows and columns that are equal, then determinant equal to 0. Okay. So first one is easier to prove. So if A has a row and column equal to 0, then you just expand on that row and column, then A equal to 0. And then the second one is harder. Now you have you have a row and a column that are the same. Then you want to see that determinant of this matrix equal to 0. Yeah. And once again, we need to prove by induction. And here the induction is a bit more complicated. So because the base case is not 1 by 1 anymore. Because 1 by 1 you cannot have row and column being the same with only 1 row and 1 column. But in 2 by 2 case, you can easily prove that if you have 2 rows are the same or 2 columns are the same, then you calculate the determinant is just AB minus AB, AB minus AB. So both the base case, you have that determinant of A equal to 0. Okay, and now we see an example in 3 by 3 case. Okay, so if you have n by n and n greater or equal to 1, what you do is so here you have 2 rows are the same. And so what you do is that you expand on the any other row that's not the 2 same row. Okay, and similarly for columns, you expand on the third column that's not the same. Okay, so if you expand on this row, then you see that it's well the element of the 3 rows. So this is minus 4, 5, and minus 6 with some minus sign, and times the determinant of the submatrix. Okay. But because you have 2 rows in here, and now the determinant of the submatrix will also have 2 rows being the same. So you have 2, 3 being same here, 1, 3 being same here, 1, 2 being same here. And yeah, so you can reduce to n minus 1 and n minus 1. And here we have a 3 by 3, so we reduce to 2 by 2, then that's base case. and we see the base case those determinants are 0, and then because the covectors are 0, your determinants is 0. Okay. Any question? Yeah. So once again, we have this induction proof that any n by n matrix, you have a 2 row and a column being the same. Then you expand on the third row and the column, then you reduce to n minus 1 by n1 minus 1 case. And so here we have a 3 by 3 is reduced to 2 by 2. Okay. Okay. And yeah, so 2 by 2 can imply 3 by 3, then we can imply 2 all the way to n by n. And so let's finish the checklist. So we have this recursive definition of determinant, and we have this covector ACIJ. So I guess it's nice to have ACIJ here again. So ACIJ equal to -1 to the I plus j times the determinant of mij. And it's important to remember that we can expand on any row in the column, and then by this theorem that we can expand on any row in the column, we prove a whole bunch of things by induction. So first is that if you have n by n matrix, then determinant of AT equal to determinant of A. And second is that A is any triangular matrix, then determinant of A equal to the product of diagonals. Okay. And third one, if you are matrix with a row and a column containing entire 0, then determinant equal to 0. And the next one is that you have 2 rows or 2 columns are equal, then determinant of A equal to 0. Okay. Any questions so far? Okay. Not. Then let's keep going. So let's look at more properties of determinant. Okay, and now we have a small lemma that's used to the next theorem, and so I guess this thing I should really write a little more. Okay, so here we have A being n by n, and and then obviously we have those AJK and ACJK, and and then now we have that for IJ, I guess IJ in n, so IJ is some index is from 1 to n. So for IJ, we have this weird thing. So we want to calculate this weird thing, so kind of subcolumn of A multiply with the covector of other column. So we have I and j might be same or different. So we have AI1 multiplying ACJ1, and AI2 multiplying ACJ2, etc. So we have AIK multiplying ACJK, and summing together. And now this is a weird thing. Okay, so we are so here's so it's ith row index, and sorry, I don't think it's ith row, so I think it's actually 1, 2, 3. So it's actually ith column. Sorry, ith column, and the the covector of j's column multiplying together. Okay, so kind of taking the inner product of ith column and j's column of this covector, those covectors. Okay. And so okay, let's go back to base case. So why do we want to do this? So if I equal to j, then obviously this is just covector expansion on the ith column, so that should equal to determinant. But what's interesting is that when I not equal to j, then we also get something interesting. So when I not equal to j, then we always get 0. and wait, I say it's a row. Wait, let me think. Sorry. Is this really row? I want. Wait, sorry, let me think a little. It's row AI. Oh, sorry, yeah, I got confused. Okay, so it's ith row and also the covector of jth row. Okay, jth row covector. Okay, so because I is fixed and we have. Okay, so we have I being here and 1, 2, 3 to m. Sorry, okay, I got confused. So we have the element of ith row multiplying the covector of jth row. Okay, and if I equal to j, this is a covector expansion on ith row. Okay, and so that's determinant of A. And then what's interesting is when I not equal to j. And it's equal to 0 because you can think of this as the covector expansion of another matrix A star. And what is A star is it's that you replace the jth row of A with the ith row of A. If you replace the jth row of A with ith row of A, you can have this matrix. So on this J, so we have ith row here. So this is ith row. Okay. So this is ith row. So on the jth row, it should be, if it was A, then it should be just AJ1, AJ2 to AJN. And but now it's A star, and A star is you replace the jth row with ith row. So now this is AI1, AI2 to AIN again. And now if we expand on this row, then you see that you exact ith row of this A star, you see that you get this expression exactly. So you have AI1 and then you take the covector, but when you take covector, you delete the jth row. Yeah. So I guess remember that you take a covector here, so I guess it's easier to see the example. So when you calculate the covector of A star on ith row, then because you deleted the ith row, so that's the same as the covector of A. Okay. So whatever element you expand on here, you always deleting this row. So you always delete the jth row here. So the covector of A star on jth row is same as covector of A on jth row. So that's just as the ACJ1, ACJ2, all the way to ACJN. Okay, and that's exactly what it is when we expand it out. So you would expand the covector of A star on the jth row. So you have A star J1, then A star CJ1, and A star J2, A star CJ2, etc. And those A star J is A star JK is just AJK because that's how we have it. So those was just AI. Okay, and as we said, the covector here is just same as the covector of A star on jth row is just as the same as the covector of A on jth row. Okay. And yeah, that's because the difference here got deleted, so the covectors are the same. Okay. And in the end, we see that the determinant of A star. Oh, I have too much C here. Sorry. Okay, so I should not have C here. So covector of the determinant of A star equal to this weird product here. And that is 0 because now we go back to look at the A star. Then you see the jth row equal to ith row. Then we from the theorem we just prove or claim. We say that any n by n matrix, if you have two identical rows or two identical columns, its determinant is 0. And here we have two identical rows, so determinant of A star is 0. and so we see this weird product between cofactor between element of I0 and the cofactor of J0 is 0. Okay. Any question? If not, then I guess we can finish this here. And now we do something very interesting now. Okay, so now we go back to the our three favorite operation and favorite matrix operation. So the three elementary operations, and then we are going to see what they do. What they do on determinant. Okay. So what we are going to do is we are going to prove these things 3 times for 3 elemental matrix. So we have a determinant of matrix multiplying on matrix A equal to determinant of your elementary matrix multiplying determinant of A. Yeah. And yeah, I guess a bit of a spoiler that this will lead us to a lot of things. And one thing lead to that's important to remember is the determinant of product of any two matrix AB equal or BA equal to determinant of B times the determinant of A. Okay, this is the end result we kind of want. But let's start with the baby steps. So first we have that we want the determinant of the third elementary matrix equal to determinant of the third elementary matrix multiplying on any matrix equal to your determinant of your third elementary matrix times the determinant of A. Okay. And let's first calculate the determinant of this elementary matrix here. Okay. And here I guess we just state here. So the elementary matrix of a third kind look kind of like this. So you have identity matrix, and you add one row of your identity matrix with some number C to another row of your elementary matrix. So you have a whole bunch of 1 here and 0 otherwhere except a C somewhere. But this is obviously always a triangular matrix, and we just say a triangular matrix have its determinant equal to the product of its diagonal. So determinant here is 1. So because the diagonal here are all 1, so determinant of this third elementary matrix is 1. Okay. And then now we can finally use our weird lemma. So determine EA, then now we expand it along J0. Okay. And then we just write down equation. Okay. Okay. And EA is this matrix where the J0 is added by the I0 by some number C. Okay. So it's AJI, so it's also AJK that was already on J0, and then with a trifactor of C, a trifactor of C times AIK. Okay. So this is J0, and so I guess I should highlight those J and I here. So we have I0 adding C times to the J0, and then here we see I0 adding C times to J0, I0 adding C times to J0. Okay. And so those are elements are getting added, and then we cofactor expansion here, then we have cofactor. And then once again, just like the logic like before, so when you expand on J0 now of EA, that's same as expanding on just A, because every other row of EA is same as A, and so the cofactor are just a cofactor of A here. Okay. Then now we just do algebra, so we expand, we multiply this out into 2 terms. So we have those original cofactor expansion. So AJK times ACJK, AJK times ACJK together. Then C times those AIK times ACJK. So we have I and J here. Okay. And then here we finally can see our lemma in use. So we have those I and J here. So small a times big A J, small ai times big A J, and the last thing we just proving a lemma. So this product sum of product is 0 for I not equal to j, and when you do row operation I not equal to j, so this thing is 0, and so you go back to the first term, which is the determinant of a. Okay. If no question, then it's time to break. And yeah, so we do go through a lot already in this class, and we prove the first property here about elementary matrix and its determinant. Okay, yeah, so yeah, let's take a 10-minute break, and yeah, see you in 11.
A star 是
哦 ，A star 是对，
为什么要用取代？
就是它是我们证明的一个帮手吧，因为我们最终是要证到这个东西等于0嘛。然后，但我们不知道怎么证。我们的方法是我们造了一个 matrix A star， 然后它的 determinant 会等于这个东西，然后因为它有2个 row 都相等，所以它的 determinant 等于0这样子。所以我们等于是从中间这个东西把2个连起来。我们有这件事情，然后也有这件事情这样子。然后 A star 的造法是，所以我们有个 I 跟 J 嘛，所以我们把dj 个 row 变成了 di 个 row 这样子。
那它这样的determinant刚好就会是刚刚那样。
determinant 会是0，因为我们之前说这个事情嘛。就是我们说，如果我们有2个 row 或是 column 一样的话，它就会这个 determinant 就是0。
我是说它的 expression 会是原本要正的东西，就是这样。
对啊，然后你从 jth row 就是你在讲的是从这里到这里啊，所以那 expression 的话会是原本的东西，是因为cofactor 会是原本的东西。例如说你算这个 AI1 的 cofactor。那你要把这个 row 跟这个 column delete 掉嘛？那你把这2个东西都 delete 掉之后 ，A star 就跟 A 长得一样，跟 A 的这2个 row delete 掉一样嘛？因为 A star 跟 A 的差别只有在这个 row 而已。你把这个 row delete 掉之后 ，A star 就等于 A 了。所以你在做 expansion 的时候 ，A star 跟 A 是一样的。如果你从这个 row 再 expand。
那所以它是第I 行的 cofactor 乘上 AC IJ。
对啊，对啊，你想要说的是什么？抱歉，第3
就是 AI1 乘 ACJ1。
对啊。
所以这是沿的那这里到这里是沿 DJ 行去展开。
对啊 ，DJ 行对，应该是行，对吧？从 A star 的 DJ 行去展开，然后 所以这个我们这里是直接写下来嘛，A star 从 DJ 行展开来，然后我们发现 A star 的 DJ 行等于 A 的 DI 行，因为我们就是这么定义的。
所以它只是把小 A I1 从 I 换成 J 换成 I 而已。
就是 A star J1 变 AJ 变 AI1 嘛。对啊，这个是因为它的 DJ 行就是 A 的 D， 就 A star 的 DJ 行等于 A 的 DI 行。然后接下来我们说 A star 的 DJ 行的 cofactor 跟 A 的 DJ 行的 cofactor 是一样的。因为你把它 delete 掉，它就变回来了。对，所以换了2次，我们把这个 star 都换掉了。然后变回来就是我们要的这个 expression 这样子，就是有对吧？就是小 a I 跟小 a I 1跟大 A C J 1这样子，就这个 I J 乘起来的东西。对，好。
这个证明它只要证说它 DI 这个元素都是相等的，那我这样写是有没有不严谨？
应该可以问一下，我准备看一下 ATJ ABAJ。你这个是小元素，我看一下。看起来没有太大的这个2个 expression 比较奇怪吧？这个应该没有太大问题啊，可是为什么你写的？这2句不太对吧？因为你这里有 k， 但是你没有把 k 加起来，你这里应该写上才对。
那要写
因为你有 k 嘛，不能就突然编一个 k 出来，然后不知道什么东西，所以这里需要写 summation。上 k， 然后我想想看，如果这里有上 k 的话，看起来就没有太大问题吧。对啊，就是这里有上就好了，这应该是对啊。 no. Hello. Oh, sorry. Yeah. Okay. Let's go back to our determinant on elementary row operation. Those results, I guess those are really all intermediate steps. We have a lot of intermediate steps, and it's to prove today. But I guess later on will be a bit more clear. Okay. And anyway, it's nice to learn proofs. So let's review of our intermediate steps a little bit. So we start with our definition, with this recursive definition of a determinant. And with this recursive definition, we see that if A has two identical row columns, determinant of A equal to 0. Then we have this, from that property, we prove this lemma, saying that if we have this weird ith row and jth row covector product, and when I not equal to j, then this equal to 0. Then, then build from this lemma, we can prove that when you do the third row operation on your A, then determinant of that matrix equal to determinant of your elementary matrix times the determinant of A. And determinant of that matrix is 1, and this will just equal to determinant of A. Okay. And this is done by doing covector expansion on the jth row of EA, and you write down the number, then you see the HR term is exactly this IJ product that we have in the previous lemma, and so this HR term is 0, so you go back to determinant of A. Okay. And yeah, so now we do row operation 3, and let's do row operation 2. And we are doing this in reverse order because we were doing lemma 2.2.1 first. Okay. And anyway, let's go back to row operation 2. Okay. We have row multiplying non-zero constant. Now this one is easier. So first we have the elementary matrix just like this. And it's easy to see, once again, it's diagonal, and you do determinant, and it will just be alpha. Yeah, because you are multiplying, you're just multiplying the diagonals, and it's just a whole bunch of 1 multiplying on alpha. Okay. And determinant of E times A. So we can just write down what's E times A, and you see the ith row multiplied by alpha, and we expand on ith row, you see that every term just multiplied by extra alpha, and so in the end you just get alpha times your determinant of A. And yeah, so once again you see determinant of EA equal to determinant of E times determinant of A. And lastly we have the row operation 1, which is you interchange 2 row. And the proof of this is I guess a bit longer. So we see how the and we actually prove this by what we have from row operation 1. Okay. So in row operation 1, remember we have that determinant of EA equal determinant of E equal times determinant of A, and also just equal to determinant of A. So sorry, so this is row operation 3. So we know that if A subtract any row to any other row, the determinant doesn't change, and we use that to to prove the row operation 1. So basically we use row operation 3 to do row operation 1 here. Okay. So what we do here is we use row operation 3 to get row operation 1. Okay. And so we start doing row operation 3 to say we now want to change second row and the third row. Okay. So we want to change the second row and the third row, and let's assume our matrix is this first row, second row, and the third row. So first we subtract third row from second row, so we get this matrix, and we never move the first row. And so the second row become A2 minus A3. And then we add the new second row to the to the third row, and so second row is still A2 minus A3, and the third row now become A2 because it's A3 plus A2 minus A3, and now become A2. Then now we subtract the third row, second row. I think the English here is English is wrong here again. Sorry. So it should be third row subtract from second row. Okay. So anyway, we subtract the third row from second row again, or add -1 of the third row to the second row. And so then this A2 will cancel with this A2. Now we have a minus A3 and A2 here. And I guess I guess we also use row operation 2 here. Okay. Also O2. Although if you are a little smarter, we don't need to use this. Anyway. And then finally we already have A3, A2 here. We just need to deal with the minus side. So we multiply -1 on the second row. Then we see that we have A3, A2 here. Okay. And so we just do this in example, but in general, we can always interchange two rows by doing whole bunch of third operation and adding a -1. I guess you also always need a second operation. Okay, you also always need a multiply -1. Yeah, and so you see that you want to interchange two rows. You just do a whole bunch of third operation and the second operation of multiplying -1. So what you get is your determinant get -1. Okay. So the first three are operation 3, and you change nothing. And on the next operation, you multiply a -1, so you get a -1 on your determinant. Okay. And in general, when you do determinant, when you interchange two rows on your matrix A, you get a -1 on your A. And you can also show that it's quite easy to calculate because the matrix is a whole bunch of 1. The determinant of this EIJ, which is interchanging IJ, the ith row and the jth row is -1. Okay. Yeah. Okay. And I guess here we use operation of is just doing row operation on the identity, and the determinant of identity is 1. Okay. Question. And anyway, people more important here is that now we remember that determinant of E times A for any elementary matrix E equal to determinant of E times determinant of A. Okay. And also, nice one to memorize here is that when you do any row operation, then your determinant doesn't change. Okay, so this one is a bit more important because it will be very useful later. Okay, And now let's see the theorem that we keep talking about. We now have the this next theorem about determinant with row operation adding on your adding on your matrix. And now we can finally prove that any matrix is singular if only if determinant is 0. Okay. And what we do is kind of natural, so we have those row operation, and then we want to use our row operation to make our matrix into row echelon form. Okay, so we know that any matrix we can do a whole bunch of row operation to make it into row echelon form, and that's what we do. So we have U is the row echelon form of your matrix. And you get this matrix by multiplying a whole bunch of elementary matrices on it. And then we are talking about determinant. So we take a determinant on both sides. So determinant U equals determinant of those things. Then we use this property a whole bunch of time. We see that when you determinant of this thing, then it's a determinant of product of determinant on everything, because you can keep taking our determinant over each ek. Okay, this is where we use the thing we just proved. Okay. And then because determinant over ek, those e don't equal to 0, just because we already see all the determinant of different type of row operation, they are all not equal to 0. So we see for the first kind of row operation, determinant is -1, and the second one is alpha with some alpha not equal to 0, and the third one is 1. Okay, so all those not equal to 0, and so determinant of U equal to 0 if only if determinant of A equal to 0. Okay. And so now we can change this condition to determinant of U equal to 0. And now we want to prove that A is singular if only if determinant of U equal to 0. Okay. And now there are two directions. So I guess we go both directions, but with the same direction, but with negation. So if A is singular or A is not singular. So if A is singular, then then what happened? We want to say if A is singular, then U has at least one row consisting of entirely 0. Okay, and that's why determinant U equals 0. And this is what we learned from chapter 1, because in chapter 1 we learned that if A is singular, then you have this free variable, and then you have this I should, let's see if this is faster if we put all the theorem just here. Chapter 1 we have anyway, while it's loading, and it's still here. Let's see if I can do this. Hopefully this don't break our streaming. So we have our theorem, let's say this theorem 1.5.2. Can I do this? And does this change? This doesn't change. Okay, this is so I need to change OBS here a little bit. PowerPoint, not this one. Too many. Oh, this one. Okay, sorry. Okay, and so remember we have this theorem for singular matrix. So we say it's non-singular if only if A is a row equivalent to identity. So it's a reduced row echelon form is identity, and also if we negate this, then we say that A is singular if only if A is not row equivalent to identity. Okay, so now we go back to chapter 2. Okay, now it's very confusing. And let's try to do this. PowerPoint slideshow. This one. Okay, now go back to chapter 2. And so we know that if it's singular, then then or U. Okay, so so I guess this is actually reduced relational form. Okay, because we want it whether it's identity. Yeah, reduced. Okay. Okay, that will be easier. Okay, so if U is REF, okay, and so we know that well, it's easier to say this one. Okay, so if it's non-singular, then we know that U is just identity. Then it's ones along the diagonal, and the determinant of U equal to 1, and 1 not equal to 0. So non-singular determinant of U is not 1. Okay. Yeah. I guess that's right here. So 1.5.2. Then we have that A singular, and so this should be colon, and A singular if only if U equal to identity. Okay, and then the easy one is A singular, A U not equal to identity. Sorry, there is a negation here. So if A is a non-singular, then U equal to identity, then we can just calculate determinant of U equal to 1 not equal to 0. And if A is singular, then U not equal to identity, then you try to write down reduced relational form of n by n matrix not equal to identity. Then you see that you must have a whole bunch of 0 at the end. Otherwise, it must be equal to identity. Okay? So this is our proof. Okay. So this is theorem 1.2.2. So anyway, I guess the result is a bit more important than proof. The result you should really memorize. Result is that matrix A is singular if only if its determinant is 0. Okay. And we have another way to calculate this. Sorry. And from here, then we have something. Okay, so the theorem, the result is nice, but from the proof, we also see something very interesting. So the interesting thing is now a way to calculate our determinant. Okay? And this is actually a faster way than doing the cofactor expansion. And that is, once again, we can use our Gaussian elimination to calculate the determinant actually. Okay? So we have that U, this is reduced relational form, equal to all those row operation matrix multiplying on A. Okay. And so if we do our row operations to reduce our A to U, then we see that well, if U is all 0, then determinant of A. Sorry, if U has a row of 0, then determinant of A is 0. Then if here it should be also be reduced. Okay. And if A is non-singular and U don't have a row of 0, then U is just identity. Then determinant of A is determinant of all those E and taking a minus 1. Yeah. So this is reduced. And so you only need to calculate what the row operations you need to do to turn your A into a reduced relational form. and then you multiply the determinant of those operations together, then you get a determinant of A. And so let's do a bit of computer science calculation here. So why do I say this is faster? Because when you have a really large matrix, n by n matrix, the number of steps you need to turn it into reduced row echelon form is about n cubed. And but if you do cofactor expansion, because it's a recursive expansion, and each recursion step you need to do about n step. So the total number of steps you need to do is about n factorial. And n factorial is much larger than n cubed when n is larger. Okay, so this is a faster way to do determinant. Okay, and yeah, and anyway, you can also do and you can also do this even a bit easier. Is that you don't need to reduce the original form to calculate your determinant. Okay? So if you want to calculate determinant, you can you can reduce A just to triangular form. So you don't need to have the upper part also become 0. So you only do half of the Gaussian elimination, and then you become the triangular form. Then you know that determinant of A is easy to calculate. The determinant of T is easy to calculate because it's triangular form. So determinant of T is just those diagonal. And then you only do operation 1 and operation 3. So determinant of A is just determinant of T with a plus or minus sign. And this plus minus sign is -1 to the number of swap you do when you get this triangular form. Yeah. Because we know that, so back to the operation here. So each addition subtraction doesn't change your determinant, and every swap gives you a -1. So this -1 to the n give you -1 to this -1 power is just -1 to the number of swap. Okay, so you can just reduce your A to a triangular form, and remember how many swap you use, and calculate the multiplication, the product of those diagonal, and then with some -1, this will give you a determinant of A. And the last example of this actually working out. So we want to calculate the determinant of this thing, and as we say, we do row operations to eliminate things. So we add this row to the -2 times to the second row, and the -3 times to the third row, and we get this matrix. And then because it's 0, then we do a swap of the second and third row, become this matrix. And now I see we are already in triangular form. So the diagonal here, the diagonals here are 2, -6, and -5. And because we swap one time, we times the -1, and the result is -60. Okay, so that's how we do this with row operation. Okay. So yeah, we see that we do have a nice way to calculate determinant with just these row operations. And then we prove another theorem. Okay. So next one, we prove this theorem that we keep talking about. That's determinant of AB equal to determinant of A times the determinant of B. And once again, this is in this theorem, it's more important to remember the result than the theorem. But anyway, so to prove theorem, once again, we need to use our 1.5.2. I guess I should really copy 1.5.2 here. Okay, and proof here. So there are two parts. So we need to. The annoying part of this theorem is we need to deal with a singular case. So if if A B is singular, then it's a weird case we need harder to prove. Okay. So if B is singular, then we need to show that then yeah, then we need to prove that AB is also singular. Okay. And so how we prove when B is singular, AB is also singular is we go back to 1.5.2. So B is singular, then there, so the first one and the second one. Wait, let's see if I can change. If I change to this, okay, yeah, we'll go to 1.5.2 here. And I guess for online people, it's too annoying to switch. So online people, please look up the slide yourself. Okay, and anyway, let's go here, and we have if something is singular, so this is A and B condition. If something is singular, then something times x has a non-trivial solution. Okay, and let's go back to chapter 2. Okay, so anyway, this is the equivalence of the condition A and the condition B of 1.5.2. Okay. And so if B is singular, then there exists x such that Bx equal to 0. Okay. And now we go back, and from this condition, we also see that there exists x such that AB times x equals 0, because this is the associative rule of matrix multiplication. Because Bx already equals 0, then multiply A on both sides, then you see that ABx equal to 0 when for some non-zero x. Okay, so there exists non-zero x such that ABx equals 0, then you go from B to A of 1.5.2, then you see that AB is also singular because you have this thing. Okay, and yeah, so this is a lot of derivation to prove the edge case of this theorem. So we see that because B is singular, AB is also singular, and B is singular, and determinant of B equal to 0 from the theorem we just proved here. And also if AB is singular, then determinant of AB is also 0. So we see this is 0 because determinant of B is already 0, and this is 0 because it's singular. Okay, so we spent a lot of time to talk about edge case. Then let's talk about the actual case. And I just realized the actual case proof is B float. Okay, so now we have B is singular, then B is non-singular, then B can be written as a product of elementary matrices. But we are mixing left and right here, so we need to do transpose here. So B is non-singular, then we actually need to do, so the proof here we have elementary matrices multiply on the right, but what we prove is actually elementary matrices multiply on left. Yeah, so we actually prove this thing. Okay, so let's do this a bit more careful. Then we need to go through a whole bunch of transpose. So B is non-singular, then we have that, so we have a delta B not equal to 0. Then we do, let's see if we can work this out. So delta BT also not equal to 0. Okay. And so B transpose is also non-singular. And then let's calculate delta BT AT, and this will equal to, then we can do this thing. So we take B transpose into elementary matrices, and this will be delta whole bunch of E's and delta A. And delta AT, and the result is yeah, so we take a BT into a whole bunch of elementary matrices, and then you do this kind of thing with the left and right inverted, and in the result that you have delta BT80 equal to delta BT and times delta AT. And finally, we use that, once again, we use delta BT equal to delta B, and delta AT equal to delta A. And so this is equal to delta AB, and this is equal to delta A, delta B. Okay? So yeah, you need to do a whole bunch of transpose to switch the left and right here, to make the theorem we have on row operations, or yeah, or you need to go back to cofactor expansion. I guess that's a bit annoying. You can go back to cofactor expansion to prove that or you also have those for elementary operation on columns instead, because rows and columns are really symmetric for determinant calculation. Okay, question? And anyway, so we have yeah, oh, well, 1.5.2 is here, I forgot, sorry. And we have our 2.2 checklist. So we have this lemma that's I guess not so important to remember. But anyway, we use this lemma to prove that when we have elementary matrix and determinant of EA equal to determinant E times determinant of A. And also it's nice to know that determinant of E is those three things. Okay. So the third one, when you do third operation, is 1. And when you do second operation, you multiply this with this alpha, and you do first operation interchanging two rows, it's 1, minus 1. And third operation is nice to remember. But all those are kind of intermediate steps to do to get the three main result we really want to memorize. Okay? And the first one here is that let's go by first one here by the ordering we write here is the determinant of A. You can calculate it by Gaussian elimination. So you do row operations on your A, and then you remember that you basically use the first one and the third one, and you just taking note of how many first one you use, and you multiply by -1, and in the end you get a triangular form. Let's see here. Okay, so in the end you get a triangular form, then you just multiply the diagonals together. Okay, so that's how we do how we calculate determinant by Gaussian elimination. And also the two main very important theorems. N by N matrix A is singular if only if its determinant equal to 0, and also determinant of AB equal to determinant of A times determinant of B for every matrix A and every matrix B. And yeah, here is a reminder. Here is all the determinant thing with theorem 1.5.2 together. Okay. And we have that in 1.5.2 we have those three things together. So A is non-singular if only if, which means A-1 exists. And this means that A is equal to 0 has only the trivial solution. Or I guess we can also write a BMO here. So we can also write Ax equal to B has a unique solution. Okay. And then third one is that A is row equivalent to identity. And now we have the fourth one, which says that the determinant of A not equal to 0. Yeah. And then we can negate everything and get that A is non-singular. A is singular means that you cannot find A minus 1 if only if A is equal to 0. It's a non-trivial solution. And A is not row equivalent to I, and also use this little more. We see that this means that A so it's a reduced row echelon form. So it's a RREFU has a row of 0. Okay, and finally this is equivalent to determinant of A equal to 0. Okay, yeah. And this will be our basis to analyze linear system. We'll see, or vector space, as we'll see later. Okay, nice to know that A is singular or non-singular, then determinant of A equals to 0 or not equal to 0, and its relation to its reduced row echelon form, or its interpretation as a solution to linear system. Okay, so this is about the linear space part, although we haven't talked about space. And if you have no question, we can talk about, I guess we can probably finish with this chapter. So then 2.3, we just have some additional things about determinant. Okay, so first we, I guess we have two more formulas, if I recall correctly. First is that there is this Kramer formula that you can use to calculate the inverse of a matrix. Okay, so yeah, so basically we can kind of solve A is equal to B by calculating determinant. But I guess a bit of a comment on this. This is not really faster than doing Gaussian elimination, because well, to calculate the determinant, you basically need to do Gaussian elimination too. But the nice thing about this is it is a closed form formula. So I guess that's the right comments here. Might be small, might be probably slower than Gaussian elimination, and but the nice thing about this is you have a closed form formula here. So let's see how this do. So and to do this, first we define this adjoint matrix. So this ADJ is it's kind of this AC matrix this covector. So the assume AC is a matrix. It's kind of like this covector from the matrix, but with a transpose. Okay, so you see that we have 1, 2 instead of 2, 1 here, and 2, 1 instead of 1, 2 here. So it's you put the covector of your matrix into a matrix, and taking a transpose. Yeah. This is we can define that as a matrix, and that matrix is called adjoint of A. Yeah. And and then remember that we have this weird lemma 2.2.1 says that AIK times ACJK equal to 0 if I not equal to J, and the determinant of A if I equal to J. Okay, and then now this is useful when this thing can be really expressed out as an element of product with your A and adjoining A. Okay, so A is this matrix with small a ij, and adjoining A with this matrix with big A c ij, and or big A c ji. So you see this 1 2 here, 2 1 here, and 2 1 here, 1 2 here, and you calculate all the element of those product. Then you see that on the diagonals you have those AI times ACI. So here you have A11, AC11, and A1 and AC1, and in here you have this A21, AC21, and A21, AC21, etc. So in the diagonal, you have those I equal to J term here, and of diagonal, then you will get those I not equal to J here. And I guess, for example, then you have this row multiplying this column, then you will have I equal to 1, and this row multiplying this column. So, so for example, we have this one multiplying this one, then we'll have I equal to 1, and this will have J equal to 2. Okay, so you see you have 2, 2, 2, 2, 2 here, and 1, 1, 1, 1 here. And we say that I not equal to J is equal to 0. So this row multiplying this column equal to 0, and this will give us this 0 here. Okay, and yeah, so you see all of diagonals are 0, and the diagonals are all the same. They are all determinant of A. That's from our lemma 2.2.1. And in the result, we have this thing is just determinant of A times the identity matrix. Okay, so we see that A times the adjoint of A equal to determinant of A times identity matrix. But then this gives us a nice way. We see that we are very close to having an inverse here, because we want something times your matrix equal to identity matrix. So you just divide determinant of A on both sides. Then we see that A minus 1 is 1 over determinant of A times our adjoint matrix. So yeah, adjoint matrix is almost A minus 1. And but this only works out when determinant of A not equal to 0. And so once again, we see why determinant of A need to be not 0 when we see again why determinant of A equal to determinant of A equal to 0 if only if A is singular. Because if determinant that A equal to 0, then you cannot calculate A minus 1. Okay, and let's see this work out in an example. So you have A equal to ABCD, then you calculate this cofactor matrix. So drawing A transpose, then it's a cofactor of this element here is just this factor D, and the cofactor of this C here is minus sign times this B here, and the cofactor of this B here is C times the minus sign, and the cofactor of D here is just this A. So we have this D minus B minus C and A here. And then we take the actual adjoint matrix, you need to do transpose, then it's DA and minus C minus B. And finally, you take the A minus 1 is you need to divide by the determinant, then it's just 1 over this AD minus C BC, and then our D minus C minus B and A. So we have the explicit formula here for A minus 1. Okay, and then we can also have an explicit formula for bigger matrix, and it will be more complicated. So we can have A equal to this 3 by 3 matrix, and then we calculate its adjoint, and then we do transpose part later. So we calculate the factor here first. And sorry, I forgot the C's here, so this should be all AC. Okay, so it's all AC here, and yeah, so you have a cofactor of this one is the determinant of this matrix, so this thing, etc. And say cofactor of this thing is determinant of this matrix, etc. So you have this huge adjoint matrix, and you see you have the minus sign on all those other elements, and then you calculate all the determinant here, and they become those things, and then finally you do transpose, and then you need to calculate the determinant of your original matrix again, and times your adjoint, then you get this inverse matrix. Okay. And yeah, so you have an explicit formula for the inverse matrix, but as we said, this is a lot of calculation, so might not be faster than doing Gaussian elimination, but it's a closed form formula. And then also there's a Cramer's rule, and it's similar to calculate A minus 1, but this is used for calculate A minus 1 on B. Okay. So you want to solve A is equal to B, and when A is non-singular, then what you can do is you calculate you can calculate each element of X with I guess this should be bigger. Okay. So you can calculate each element of X as delta of AI delta of AI divided by determinant of delta of A, and where AI is this weird matrix. AI is the matrix obtained by replacing the ith column of A by B. Okay. So you have B here, and we can replace every column of A by B, and having that AI. And you calculate determinant of AI divided by determinant of A, and that will be the ith element of your X. Okay, and here we can have a bit of a proof. So X is A minus 1 on B, and we already have the formula for A minus 1 is 1 over delta A times adjoining A, and it's this thing, so 1 over delta A and adjoining A on B. And we want this thing to equal to x1 to xn, and so if we look at some xi, okay, and some xi, it will be the ith row of this adjoining C times this B. Okay, just look at the matrix multiplication. So ith row of X is all those B times those covectors. So the ith row covectors here. So AC ith row of ADJA. So AC1i, AC2i, etc. And then then this thing will equal to delta AI by the similar calculation we do when we do lemma 2.2.1. So we see this matrix AI is the ith column replaced by B here, and if we expand the AI on the covector expansion AI on this column here, then we see that those elements here will be yeah. So the elements here will be just those BK, so B1 to Bn, and then the covector will be same as the covector of A, because when you expand here, you delete this column, and the covector of AI will be same as covector of A on those columns. So it's just A1i, A2i, etc. So you see this thing is same as the determinant of AI. Okay, so we prove that this equals determinant of AI, and so xi is determinant of AI divided by determinant of A. So now we also have a closed form expression of X. We have that every element of X is this ratio of determinant. Okay. And yeah, so that finish this chapter. So this checklist for 2.3, we define the adjoining of A is this AC with the transpose. Okay. So we write down the covector matrix, and then we have two closed form formula for calculating A inverse and AX equal to B. Okay. And so it's these two formula. A minus 1 is 1 over determinant of A times this adjoining matrix A, and xi is determinant of AI divided by determinant of A, where determinant of A, where this matrix AI is A with ith row, ith column replaced by this B vector here. Okay. Yeah, we are exactly on time. And if there is no more problem, then we will go on our chapter 3 starting this Wednesday. And yeah, I guess we'll have a lot of Wednesday class for the next few weeks because we keep having holidays on Monday. Okay, so see you on for Wednesdays. Oh, yeah. Oh, I guess 下个礼拜一我们还是有课，对不对？记一下。下个礼拜一还有课，然后接下来2个礼拜一就没有课了，看起来是这样子。